Karim, can you share the slides? So the recording started. Great. So let's start. So it's a great pleasure to have Karim. Thank you very much, Karim, for making time for this. So today we have Karim Abadir and we have Christian also as a panelist. So Karim will present explicit minimal representation of variance matrices and its implication for dynamic volatility models. So you have 1 hour, and we might, people might interrupt with the questions. So everyone is welcome to ask questions. Either, if you prefer, we can unmute you and you can ask your question directly. Or if you prefer, you can post your question in the chat, and then we can read it on your behalf. So thank you very much, both of you again, and the audience for attending this. And you have the floor is yours, Karim. Thank you.
Thank you, Abdurrahim. Sorry, I'm recovering from a flu, so my voice may give up at some point. I was telling the organizers this is an old project of mine. I was working on distribution theory a very long time ago, and I was interested in representation of orthogonal matrices because of integration over spaces of orthogonal matrices and so on. But I never really considered doing anything with that until the book with Jan Magnus on matrix algebra was completed in 2005. Then I left York and went to Imperial, and this is where things slowed down considerably. And I only finished that the first version of the first paper in 2016, which then came out in the Econometrics Journal. And now I'm writing a follow-up with Michael Rockinger, who's here in the audience, which is in many ways more interesting because it's got a more global perspective. So let me start by motivating why I'm doing this. And time-varying volatility models are used in a lot of applications. And in particular, conditional heteroscedasticity, but not exclusively. There are other applications to stochastic volatility and others. The multivariate extensions are important because empirically we're dealing typically with many theories and we want to be able to model them jointly. The problem is we need a number of features that are present in some models but not others. The first feature we need is positive definite matrices that are explicitly obtained from the model, not by trial and error, and not by generating matrices that are non-definite and then discarding them. We also want models that cover the full space of positive definite matrices, not just a subspace of that. And I will show you later on in the talk that some quite popular models are actually not covering the full space that we need. Now, if you got a model that's over-parameterized, it becomes really hard to estimate it in high dimensions. So we need to really focus on models that are enabling us to estimate an unrestricted version of the variance matrix dynamics. And more fundamentally, we want to reduce the number of parameters to the minimum, and as a result, reduce the dynamic processes that you model to a minimum, so that you don't have too many things to estimate that you don't need. And on top of that, you're able to estimate them in a big dimension. So the contributions are as follows. First of all, we abstract from any dynamics. We just look at what is a variance matrix, and we represent it explicitly. And in doing so, the positive definiteness reduces to k-easy univariate conditions. So it's not a complicated interaction of coefficients and variables such that you want to find what's positive and what's not. And as a result, we use it to specify multivariate heteroscedasticity models, which we call dynamic spectral heteroscedasticity, DISH. And the number of variance covariance parameters is reduced by about a half. And we get the most parsimonious formulation that you can have for a general variance matrix without any restrictions. General meaning that you can cover the space of variance matrices without having to do trial and error. We then apply this decomposition to the case of conditional heteroscedasticity. And as a result, we apply to what we call dynamic spectral conditional heteroscedasticity and dynamic spectral conditional correlation, DISH and DISC. We introduce a new criterion because we want to be able to say how much any model covers the maximum allowable. And the maximum allowable turns out to be a space that is called elliptopes that are positive definite of dimension k. So that's the k. E is for elliptopes, and the plus is positive definite. The notation varies. So in some cases, you find double plus to stress that it's a positive definite rather than semi-definite. But I use different notation for positive semi-definite, 0 and plus as a subscript if it's positive semi-definite. And we show that our model achieves the maximum benchmark by construction and for any dimension. However, a model like dynamic conditional correlations, DC, for a case of, for example, k is equal to 3, will only achieve half of that coverage. So this is a very popular model, which unfortunately doesn't get up to the maximum that can be done in terms of correlation matrices. And to show empirically that it makes a difference, we apply to construct minimum variance portfolios over time for up to 1,000 stocks. So it's a large application. And we attain consistently higher returns and lower risk than the best of DCC-based methods. So it's not just a theoretically interesting result, but it's also practically useful. So let me start with a few definitions. Right. So let's define sigma to be the variance matrix and define the matrix exponential function as usual infinite series. And in practice, you don't need an infinite series. You need a polynomial of order k minus 1. And we go through that decomposition using Jordan's, or calculation using Jordan's decomposition in the matrix book with Magnus in 2005. But here we need a simpler case of this matrix function. And this is the simpler case that we need. So upsilon is a non-zero skew-symmetric matrix. A skew-symmetric matrix is defined such that the transpose is equal to minus the matrix. Just to give you a very simple example of a 2x2 case, it's a matrix that has 0 on the diagonal, and whatever is on the upper triangular part is reflected with a negative sign below the diagonal. So it's a matrix with whatever you want to have in the upper triangle, and in the lower triangle, you get minus that quantity. So what does the lemma say? It says that the spectral decomposition of upsilon has this form of the exponential of upsilon, has this form. And lambda are the eigenvalues matrix, or if you work out what these eigenvalues are, you get into some details that I'm going to avoid here, but it's in the original paper in the Econometrics journal. And basically that thing in the middle, the exponential of the block diagonal matrix, can be written in terms of blocks of cosine and sines with angles theta I up to k over 2 or the integer part of k over 2. So basically, it's a sequence of rotation matrices. So that's a technical lemma that I don't want to dwell on, because what I really want to dwell on is the next one. And the next one is a very useful representation that allows us to write any orthogonal matrix in a very simple representation. The problem with orthogonal matrices is you need to solve a bilinear equation. Q prime Q is equal to an identity matrix. And that is not easy to formulate and solve. So how do we simplify this problem? That lemma simplifies the problem by providing an equivalence. The first part of the equivalence is easier to establish, and it gives you the intuition. That's why I write it out explicitly. It says that the exponential of any skew-symmetric matrix is going to be an orthogonal matrix that has determinant +1. That's a proper orthogonal matrix. And part 2 of the lemma establishes the equivalence, or the reverse implication. So let me start by taking this e to the upsilon, transpose it, and I want to show you that it's equal to the inverse of e to the upsilon. And the reason is the definition of an orthogonal matrix is that the transpose is the inverse of the matrix. Okay, so e to the upsilon transposed. Upsilon prime is, because upsilon is a skew-symmetric matrix, upsilon prime is equal. The result, the transpose is simply the inverse once we exponentiate. That it has a positive determinant of +1 is established by taking the determinant of that and using this relation from determinants of exponentials. We show that the determinant is +1. So it's a proper orthogonal matrix. Why is this nice? Because that Q that has this horrible restriction, Q prime is equal to the identity matrix, is really hard to solve. And it's not explicit and it's nonlinear. On the other hand, the upsilon matrix, the skew-symmetric matrix, is really nice because anything above the triangle is replicated below the triangle or below the diagonal. The upper triangular and the lower triangular are the same thing with a minus sign. And whatever triangle you choose, the parameters are free to vary from plus to minus infinity. So the nice thing is, first of all, you reduce the problem to the only free elements that you're dealing with, which are k minus 1 over 2 elements. And you have total freedom in letting these elements go from minus infinity to plus infinity.
So, sorry, can I ask a question, Karim?
Of course, yes, Majid.
But an orthogonal matrix can also have determinant -1.
Exactly, yeah. So that's the next slide.
Okay, sorry.
You're one step ahead of me. Yeah, no, it's a valid point. So the next slide says, okay, if that is the case, if we want a diagonal, sorry, if we want an orthogonal matrix that has -1 as opposed to +1, you use a permutation matrix in the first block here. The determinant of that is equal to -1. So p to the power delta, if delta is equal to 1 times e to the upsilon, that is a Q matrix that has determinant -1. Is that okay? No. So any variance matrix by the usual spectral decomposition has a diagonal lambda with a positive diagonal and an orthogonal matrix and its transpose. Remember, the transpose is just e to the minus upsilon because of the skew symmetry of upsilon. So now we've reduced the problem of a variance matrix, which has almost half the parameters that are redundant, to one where we have k parameters, which are the diagonal eigenvalues, and the upsilon matrix, which is basically k times k minus 1 over 2, and the sign switching matrix for the determinant that precedes this e to the upsilon. So that represents any variance matrix with determinant plus or minus 1 in the orthogonal component. So that first feature we mentioned already. It is convenient because instead of having an orthogonal matrix whose parameters are non-linearly restricted and there are k square of them, you have an unrestricted k times k minus 1 over 2 specification. And the positivity restrictions are straightforward. Eigenvalue is positive, and that's easy. Don't have to solve any complicated nonlinear things. There's an alternative specification for orthogonal matrices in terms of a sequence of rotations, and there's a section in my statistics book with Heymans and Magnus on that. It's not going to be very convenient, also because the angles are restricted and so on. So it's really the representation of the previous slide is the easiest that one can find. It is possible to enforce in a decomposition that the eigenvectors give you orthogonal matrix of determinant plus 1. But if you do that in a dynamic context, it's going to lead to discontinuities in the time path of the upsilons, of the elements of the upsilons, which are denoted by this. So even though it's not a necessity to have a delta in the static representation, in a dynamic representation from a modeling point of view is really convenient. Otherwise, you'd have to model jumps in the process. So going to the class of dynamic models that we want to analyze, we just make the conditional variance time dependent. So we take the representation of that proposition and put subscripts t there. There are 3 components that we need to model over time, which is the eigenvalues, the upsilon t, which are really nicely modeled because now they're totally free to vary unrestrictedly in the real line, and the delta t, the switching deltas. Delta is 0, 1. Delta is binary. But before I do that, let me just write the usual specification for conditional variance models or conditional heteroscedasticity models, which is using the square root of the variance matrix. And this is the symmetric square root, which is given in equation 6. If you multiply it by itself, you recover the sigma. So the only place where you really have a square root is the diagonal, the square root of the diagonal elements. Now the 3 dynamics model. First of all, the diagonal dynamics are straightforward if you normalize the x vector, if you rotate it by the orthogonal matrix. Then you've got a z vector which has a conditional variance of lambda, and this can be modeled by a traditional gauge, E-gauge process. So equation 8 is a gauge, equation 9 is an E-gauge. And because we assume normality, then there's no loss of generality from modeling component by component. If you assume another distribution for the epsilons, then uncorrelatedness and independence are not the same, in which case you need to model the multivariate system as in 8 or as in 9. G is a asymmetric sign, asymmetric absolute value function. So it's straightforward generalization of the univariate case. Now, if you raise a matrix to an exponential in order to recover the lambda from equation 9, you have to be careful, because if the matrix is not diagonal, the exponential of the sum of 2 matrices is in general not equal to the product of the exponentials. Luckily, the two matrices are diagonal, therefore they commute, and as a result, the exponential can be broken down into 2 separate exponentials. The second component is a bit trickier. The second component is the upsilon, the skew symmetric. So let's go back to what we want to model. It's the quadratic quantity of interest whose expectation or conditional expectation is leading to the conditional variance sigma. So that quadratic function, we want to decompose it and extract the component that we haven't used yet. The decomposition of xx prime is given in equation 10. The eigenvalue component, because it's a matrix of rank 1, it's got 0 eigenvalues k minus 1 times, and only one non-negative, positive, actually, eigenvalue x prime x. X prime x is an information we have already used. So basically, the diagonal component is not of interest to us anymore. It's the orthogonal component that is of interest. And guess what? Upsilon is also exponentiated to give an orthogonal component. So upsilon and q are going to be linked up. But upsilon was obtained as the log of an orthogonal matrix, or in other words, e to the upsilon was orthogonal. So let's take the log of the orthogonal q that we had in equation 10, gives us a Xi matrix, a data matrix, that we can then put in an ARMA process for the elements of upsilon. So the elements of upsilon are related to their past, and they're related to the other skew symmetric component that we got from the data from equation 10. Obviously, this is a simplification. We can have more lags than one, and we can have things other than ARMA. We can have interaction between the components, not just by exponentiation, but also having a system, a Varma system for these upsilons, if we want. And finally, the delta, the sign switching components. So let's put all these things together. First of all, in the sigma matrix, we've got a process for the upsilon. We've got a process for the lambdas. Let's call theta the parameters of these processes. Let's put them all in a big vector. And then, because we've assumed a normal likelihood, this is Jacobian of the transform, but even without assuming a normal likelihood, this is the log likelihood of the density of the epsilons. The Jacobian of the transformation involves the lambdas, and because the orthogonals don't make a difference to the likelihood, it's the lambdas that make a difference. And as a result, optimizing this log likelihood will not only give you the optimal values of the parameters theta, but also whether the sequence of deltas is zeros or ones. Now, if you want to make a forecast out of sample for these deltas, then you can assume a number of possibilities for that process. And that is done in the already published econometrics journal paper. And a very simple but very effective and reliable process is a Bernoulli process, which is basically binary, 0, 1, with different probabilities. And these probabilities can be obtained historically up to the point where you want to make the forecast, then projected onto the next data point, deciding whether delta is estimated as 0 or 1 or forecasted at 0 or 1. Now, this was about the sigma matrix, the variance matrix. If you want to estimate a correlation matrix, then basically you've got to use the usual normalization. That's just the definition, really. Nothing new there. And if you want to model something more special, like partial correlations or conditional correlations, conditional meaning 2 dimensions, conditional on the rest, then you need to invert the sigma matrix and take the off-diagonal element of that sigma matrix, put a minus in front of it, and divide by the square root of the 2 diagonal corresponding elements. This is what is called the partial correlation. And because of the decomposition we've adopted, it's really trivial to calculate the inverse of a matrix in a fraction of a second, because You've already got the exponentiation of the epsilons. You've already got this sign switching if needed. All you need to do is to invert the diagonal elements of the lambda, and you've got the inverse of the sigma matrix. So matrix functions are really easy to calculate within this context, and it's not just the inverse. There are all sorts of other. Square root is another example we saw a few slides earlier. You can calculate any matrix function in the blink of an eye. Now, you may say that if we are interested in equation 15, correlation matrix, then there are k-nuisance parameters, and these are the variances, the diagonal elements. If that is the case, if you're not interested in diagonal elements, then you can use one of the modified likelihoods as opposed to straightforward likelihood as on the previous slide. The modified likelihoods have been really nicely summarized in a book by Severini already 23 years ago. So you've got the bound of Nielsen modified likelihood. You've got lots of different modified likelihoods that you can consider if you want to get rid of these k-nuisance parameters. Okay, so now an interesting new section which gives us a broad overview. How good is a variance? How good is a dynamic variance model? Because really, I mean, we've got a proliferation of lots of dynamic variance models, but we don't know how good they are. Do they cover the whole space of variance matrices? Do they have gaps in them? How big are the gaps? So this section is trying to get down to an answer, quantifying an answer to this question. By definition, and we've seen in the lemma 2, which gives the equivalence of the representation, and proposition 1, which gives the explicit representation of sigma, we cover the space of positive definite matrices, which is denoted by S plus K. And the corresponding normalization for variance for correlation matrices omega is covered. The elliptopes of dimension K, positive definite elliptopes are covered. Now, before I go on to analyzing something like a DCC model, I want to see what is a measure of shortcoming or lack of spanning that a model can suffer from. So let's take any correlation matrix omega that is positive semi-definite. Then the eigenvalues are between 0 and 1. And therefore, the sum of the eigenvalues is a bound for the largest eigenvalue because there are no negative lambdas. So if you set all the lambdas except 1 to be equal to 0, then the bound on the remaining eigenvalues is just equal to k. K is the dimension. So this is a sharp bound, the bound that is attained if you want to cover positive semi-definite correlation matrices. And this proposition shows that DCC models, whatever the DCC model specification, whether it's the ILE modification or the original one, whether it's a 1-1 dynamic, 1-1 lag model or PQ lag model, all of them have a restricted range for the eigenvalues. And that is a proper subset of the allowable range, which is 0 up to k. As a result, because of the eigenvalues also not covering the full range, the eigenvectors will also not cover the full range, and the angles that you're going to get from these things will not span the full angles that you can span, neither statically at any given point in time t or as you move across time. Now, numerically, let's see how we can quantify this, because this is just telling you what the limitation is. How bad is that limitation? So up to now, we're not aware of any numerical criterion to evaluate the coverage or the span of models of variances and covariance and correlations. Sorry. So let's focus on an example for the case of k is equal to 3. The measure that we're going to present is actually a general measure, but graphically it's nice to present, and numerically it's nice to present it for a three-dimensional case. So let's look at an omega matrix, correlation matrix that has ones on the diagonal. Off-diagonal correlation between first and second component is omega 1. First and third component is omega 2. Second and third is omega 3. The condition for this omega to be positive definite, not positive semi-definite, is in terms of the principal minors. For positive semi-definite, you need all the minors, not just the principal minors. So what is the condition? The condition is obviously in dimension 1 is a trivial one. In dimension 2, in dimension 1 is just that. In dimension 2 is just that all the omegas are less than 1 in absolute value. In dimension 1, just 1 is positive. In dimension 2, 1 minus omega 1 square says that omega 1 has to be less than 1 in absolute value. Then you get to the three-dimensional case where the determinant has to be positive. And the determinant positive implies that we need this condition. Now, the limit of this condition, the point at which this condition breaks down, is when this is equal to 0 and this determinant is equal to 0 instead of being positive. So the boundary of this condition is what we're going to trace next. And we're going to see how close to the boundary any variance model is. So let's do it explicitly. The solution to omega is equal, determinant of omega is equal to 0 is a quadratic, which is solved by the usual discriminant term here. And that discriminant term gives you a space which is bounded by these two square roots. If you integrate that space out, you get the volume that is covered by these ellipses or by these elliptopes of dimension 3. And the volume in the three-dimensional cases can be obtained explicitly by using the integrating constant of the beta density. And notice that if you've only got omega 2 and omega 3, this discriminant here reduces to the two components of an ellipse, the upper component and the lower component. And that's why the general equation number 18 leads to something that is called an elliptope, a generalization of an ellipse. And this is the elliptope. The elliptope is a funny creature. It gives you the maximum that you can reach in terms of combinations of correlations. The axes are omega 1, omega 2, omega 3. And these circles and ellipses are slices that you take for the case of omega is equal to 3. That's the black circle. Omega 3 is non-zero, is 0.25, gives you the blue one. And the red one is obtained for omega 3 is equal to 0.75. The reason they are inclined is because the graph itself is inclined. So you've got the omega 1, omega 2 axes at the bottom that are not that are tilted towards the bottom a little bit. So focus on the upper part of upper half of this graph. Forget about the lower half for a minute. Start with a black circle. As you move up, this black circle gets twisted into an ellipse and gradually twisted into the very top. At the very, very top, you find a very thin ellipse. So this is the elliptope top half. The elliptope bottom half is exactly the same thing, but twisted with an ellipse pointing in a negative direction as opposed to the positive direction. The top ellipse is basically giving a positive relation between omega 1 and omega 2. The bottom ellipse is giving a negative relation between omega 1 and omega 2. Because at the bottom, omega 3 is negative. By the way, this is, if you focus on the upper half of this graph, it's a shape that you've already seen many days in your life. This is an everyday use of a half elliptope, if you wish. If you go to the Plum Center and ask for top half of an elliptope of dimension 3, the guy will know exactly what you mean and will give you this sync plug. So there you are. You will not forget about this one easily. Let me share a different graph. Share screen, this figure. Right. Can you all see the figure? Okay. Right. So this is the elliptope. If I make the omega-1 or omega-2 axes perfectly flat so that you don't see them, it looks like a sequence of cuts of the surface. And basically, when you're integrating to obtain the volume, you're calculating the surface of the cuts or the slices. So you're calculating the surface of the black circle, then the blue, then the red ellipse, and you're accumulating all these to get the volume of the object. Just to show you at the bottom, it's going in the opposite direction from the top. Okay, so there we go. Okay, so that's a little bit of fun there. Let's go back to the talk. So we take DCC with parameters alpha 0.3 and beta, the rest up to 0.9998, which is extremely persistent, but not as much as an integrated DCC. And beta is the autoregressive parameter in the DCC, whereas alpha is the one multiplying the data. So we do that so that we get as much variation as possible in the time path of the correlations, which we are going to summarize below. We also tried a normally distributed epsilon as well as a student T with fat tails. Didn't make much of a difference. Didn't make much of a difference to the coverage or the span of correlations. It makes a difference to other things, but not to the span of the correlations. We chose S, the constant matrix of the DCC, to be an equicorrelation matrix, taking one of 3 possible values, small correlation, a higher one, medium correlation, and then a larger correlation. Anything bigger than that is actually worsening the coverage, and anything less than that is reverting you to some IID process, which is not very good. We iterated 400,000 steps and looked at the time path of correlations to try and summarize what kind of correlations a DCC can cover. Then we did the kind of partitioning that we saw in the previous picture, where we partitioned omega-3 into a sequence of slices for between 0 and 1. These slices are not very thin. They are thickness of 0.125. And the negative values of omega-3 and the positive ones are basically symmetric. I think there's a question in chat. Let me see.
No, that's just a reminder,
no, okay.
Karim. No, don't worry. We're going to control that. Thanks.
Okay, very good. Thank you. Okay, so these are the slices now. Every row is a slice like the circles and the ellipses that we had. And this is the maximum coverage given by the elliptope. And basically, if you sum all these elements in this column and you multiply it by the width of the slice, which is 0.125, you get that V3 figure that we had approximately, because the slices are not super thin, they're a bit thick. But if you want to get closer to that number, you would reduce the thickness of the slice. So what do we get for DCC for 0.3, 0.5 correlations, so on? Well, it looks like the extremes, when you want to get to really high correlation, are not well represented in the DCC model. And the intermediate value of S is 0.5 is the one giving the best coverage. But even so, if you compare the maximum coverage, the surface of the slice that is close to the top of the elliptope, if you compare it in the case of the elliptope with the DCC, you get quite a big gap. You get a gap of 0.93 to pay. It's almost double, basically. So almost half of the space is not covered when you're talking about a high value of omega-3. And these are the slices illustrated for one of the values of S. So Michael calls it the salami graph. So the red bits are the coverage of DCC. And there's a MATLAB function that actually allows you to draw the limit of a coverage, a convex hull. And this is the curve surrounding the red dots or the red crosses. That's what DCC gives you. And the green is basically the elliptope. And the elliptope has also a convex hull outside, which is bigger than the one inside. You can see when omega gets to a big number, when omega-3 is, let's say, 0.9 or thereabouts, you can see that the coverage gap is quite big. This is what we saw in the table also.
So is there a way to like test, but also like there is a something that can tell us that this is an acceptable level? Like we look at a model and say, okay, this one is doing a good job, and the other one is not. So you see what I mean? I mean, of course, we have this maximum amount. I guess maybe there is a way to build the test to see how much we are close or far away, because that's a data.
So if you accumulate these columns and you multiply by 0.125, you get an approximate value, which we calculated in the paper for these various values, and compare that to pi square over 2. And then you get a measure of the deficiency. But you're asking about the empirical question. So, for example, it may be that we don't need the very high correlations, in which case this is not so important. It may be that we have a system where we get nicer behaved set of correlations over time, in which case we're closer to the middle of the graph. You still see a deficiency. And that deficiency is a reflection of the proposition that I showed you, which shows that DCC models are inherently not covering the space, whatever correlation you want to imagine. And how big the problem is an empirical question. If the DGP, I mean, it relies on not knowing what the DGP is. So if the DGP is this one, then you're in trouble. If the DGP is that one, then you're in less trouble. So it's the actual impact is very much dependent on what the true DGP, unknown DGP is.
Yeah, and a very bizarre question. I think that's maybe it doesn't make sense, but because you will have an application to portfolio, right? And when we talk about portfolio, we talk about diversification, we talk about correlation, right?
Yeah.
So I'm wondering whether there is a way to connect both and, try, I mean, whether it can help like to choose the right, I mean, you fix the you focus on the performance of the portfolio, okay?
Yeah.
And say, I want to maximize that. And then I mean, you maximize that in a set of models of volatility. I don't know whether it makes sense, but you see what I mean? It's
So the next section is going to show you what is the performance like. But from this picture that you've got in front of you, it says that in quiet times, you probably don't have a huge loss. But in turbulent times where you get really high correlations and all the stocks are crashing together or all of them are jumping together, then you really have a problem because a model like DCC will not be able to catch that.
Thank you.
And just to give you a more detailed picture of one of the slices, here's one. Okay, so let's go to the portfolio application. I think I'm okay for time. Good. Okay. So we follow Donald Ledois and Wolf in the 2021 Journal of Financial Econometrics paper, where they look at a portfolio of size 100, 500, 1000. Then they do a portfolio allocation, and these are assets coming from New York Stock Exchange, Amex, NASDAQ. The only difference is we take a more recent data set that goes from 1980 to last year, and these are daily observations. They do a horse race and they find that the best model is a factor model based on DCC nonlinear shrinkage. And this DCC nonlinear shrinkage is a model that was in Ledois and Wolf 2019 Journal of Business and Economic Statistics. So that becomes our benchmark. We don't recalculate all the models. We take the best performing model that they had, and we compare what we get from what they get. We estimate the models on the most recent 5 years, so that's 1,260 days, and we perform a 1-month forecast. So we perform a forecast of the 21 days in the next month, and we calculate the performance of that forecast. Then we go re-estimate everything again 1 month later and redo the same exercise and so on and so forth. And what is the performance that we get in total? The Ledois and Wolf is the solid line at the bottom. And this is the cumulative performance. If we let the eigenvalues follow a gauge process, then it's the dashed line, dash dotted if we let our eigenvalues follow an e-gauge. And the very last one at the top is if we let the eigenvalues follow an e-gauge, but take the average of the previous month as opposed to a pure e-gauge day-by-day process. And you can see that it's there's no point at which these are crossing. In fact, it's more than that, period by period we're dominating in terms of returns, but also in terms of risk. Let's zoom into this latter part and give you a clearer picture. By the way, look at the scale of these numbers. They're quite big, 10 to the power 4. So let's zoom in to that last section. And that includes a lot of dodgy periods like the Great Financial Crisis, taper tantrum, COVID, etc., etc. And you can see the gap in performance is notable. So in terms of tables, we summarized in 2 tables, one relating to turnover and to shorting and so on, which is at the bottom, and one relating to the average gain, the standard deviation, and the information ratio. So these are the measures they use. We also include the 1/n. 1/n is basically you distributed, you distribute equally your portfolio over the stocks, whether they're 100, 500, or 1000. The equal weight is got a really high average return, but it's a very dangerous portfolio because it's got a really high standard deviation, and the result is the information ratio is quite low. In terms of returns, you can see that the DSCC models are doing quite well. In terms of variance, the EGARCH is doing quite well. And the reason for the EGARCH is basically the lambdas are something between something that is positive. A percentage change in the lambdas is the best process to use rather than a GARCH. So EGARCH is better than GARCH for the lambdas. And you can see that it's got the lowest standard deviation across. In terms of information ratio, it's got one of the best information ratios. The one that's better than it is if you average the last month's observations. Turnover is low for the equal weight portfolio. It's higher for the other ones, but it's reasonable. It's not too bad in the case of the DSCC. And these are the shorting percentages in the last column. So there's no shorting in the equal weight. Gross leverage is the middle column. And you can see that it's more or less comparable, except that we don't short as often as the DCC model. So I guess I'm a few minutes ahead of schedule. That was the last slide. I'm happy to have questions now if you wish.
Thank you very much, Karim. So yes, we still have a few minutes before the. So if you have any question, Karim, the air conditioning is not an issue here because the papers that you mentioned, they generally have an issue with, like, I guess these are portfolios that need the variance covariance matrix to be inverted, right?
Yes. So DCC will not lead to non-negative, non-definite matrices. That's for sure. But then if I'm talking of Beck or something else, then yes, we have a problem. We have to do trial and error. We have a lot of redundant parameters, which limits. You cannot possibly estimate that model in the case of 1,000 stocks. It's way over parameterized.
Okay. So let me stop the recording and then.
Christian has a question.
Yes. So and then we can allow for.
Yeah. Thanks, Karim. Very interesting talk.
Yeah.
I have a question.